Hello everyone. Today my teammate Rawa and I will be presenting and demonstrating our real-time data streaming pipeline projects. This pipeline captures cryptocurrency price data. It streams it through various components and ultimately stores it in a data lake, all while capturing any changes that occur along the way. So before we start executing the commands, let's me explain the architecture of our pipeline. So as you can see here, the pipeline consists of five main components. We have the first container, which is PostgreSQL, and this is where our cryptocurrency price data is initially stored. It is configured with logical replication enabled, which is essential for capturing data changes. And the second components, we have Debezium. This is a change data capture tool that monitors PostgreSQL's transaction log, and it can detect any inserts, updates, or deletes happening in the database. Sorry. So now let's move on to the third component, which is Kafka. And this messaging platform receives change events from Debezium and makes them available to downstream consumers. So it acts as our real-time data highway. For the fourth component, we have HDFS, and this is our data lake where all changes are stored in single sink file per partition, and it allows for easy analysis of the full history of data changes. And we have Hive, which acts as data warehouse layer that allows SQL live queries on the data stored in HDFS. And it has two components, Hive Meta Store and Hive Server. And finally, we have a tool that orchestrates the entire pipeline, which is Airflow. It schedules and monitors tasks to ensure everything runs smoothly. The key feature of this architecture is that each component runs in its own container, allowing them to be deployed and scaled independently on different machines or clusters as needed. So as you can see, this modular approach makes the system more robust and maintainable. Now I will start each service one by one using Docker Compose, and this will demonstrate how each component runs in a separate container. So now, since we have changed the directory to be in the folder projects, the root folder, so now we will start our Postgres container, and this command launches a PostgreSQL database configured with the logical replication enabled through the parameter which is called wall dash level equals to logical, and this setting is crucial because it allows Debezium to capture data changes. And next we'll source Kafka and Zookeeper. Let's look at for the command that will run this Kafka container. This is the command that will run it for us. So let's create the container Docker, and so Kafka here will handle all the change events as messages, and it is configured with multiple listeners to allow both internal and external connections, which is really important for distributed systems. Let's run Hadoop now. We have used this file to facilitate copy paste for the running commands, especially for the Docker Compose to push our containers like Hadoop, PostgreSQL, and Kafka containers. And as we can see, the Hadoop container started successfully, so we will be moving to our Docker Compose file for Hadoop. This is our Docker Compose file. As we have seen in the console, it launches actually 4 nodes. We have the NameNode, DataNode, Hive Metastore, and the Hive Server. for the NameNode and the DataNode services for HDFS. So we have the NameNode, which actually manages the file system namespace, while the DataNode only stores the actual data. And for Hive Metastore, it actually stores the metadata about Hive tables, partitions, and some other things, while the Hive server provides service interface for the client to execute queries. And now let's move to Connect. We will start our container. We just wait for the container to be started and move on to the Docker Compose for Connect. And basically this container includes both the Debezium PostgreSQL connector and the HDFS Sink Connector. They are pre-installed as specified in our Docker file. And these connectors will handle the data movements between all our services. Now let's start Airflow. So we'll copy the command that will for the Docker Compose of the Airflow. So all the containers must be created and started. As you can see, they all started successfully. Now let's move on to the Docker Compose for Airflow. With this Docker Compose, Airflow will orchestrate our entire pipeline because it consists of a PostgreSQL metadata database, a scheduler, and a web server for the UI, the user interface. And now let's see from Docker Desktop how all containers are running independently, as they should, of course. So it shows them with green color, meaning healthy states, which is a good sign for us. We can also check from the command line which containers that are really running, and we got the same thing as the Docker Desktop. And let's just fix this. Okay, so now we'll create our connectors, and we'll just copy the command that is responsible for that. So let's take the command that will let us create a connector. So we have here under connectors the Debezium PG source and HDFS sink, and this is the HDFS sink JSON file, and this is the Debezium PG source JSON file. And in the config tag we have the key configuration points. Firstly, we have connector.class, and it specifies the PostgreSQL connector class. Then we have the database.hostname, ports, user, password, which are the connection details for PostgreSQL. We have table.include.list. It limits which tables to monitor. In our case, we have only the crypto prices. So then we have plugin.name. It says to PG output, which is the PostgreSQL's native logical replication. Then we have slot.name and the replication.name. It references the logical replication slot and publication. And lastly, we have topic.prefix. This is the prefix for Kafka topics where changes will be published. And now, since we have created the Debezium connector, we will create the HDFS connector as well using this command line, and everything will be registered in our local machine using localhost. And before going further, let's see the contents of HDFS Sink JSON file as well. And these are the important settings. It includes the connector.class as well as the Debezium config. which specifies the HDFS Sink Connector. We have the topics, the HDFS.url. This is the HDFS NameNode URL. We have flash size and the formats.class. It uses JSON formats for the output files. And now let's see if our connectors are published. And we can see both of them. Now let's see their status as well. And as we can see, the Debezium is running. Now let's see the HDFS sync status, and it is running as well as the others. So thanks for that. I will let you with my teammate Rawa, and she will explain the rest.
So at this stage, let's go deeper into our pipeline and demonstrate its work. But first, let's check if all the containers are working properly. And as we can see, they are all green, which is a good sign. We have the Postgres, as well as Zookeeper, Kafka, NameNode, DataNode, Hive Metastore, and Hive Server, and all connects, and all the components of the Airflow, which are Postgres Airflow, Airflow Scheduler, and Web Server. All right. Now, how the data is injected and how the test is done automatically. To do so, we have created two Python scripts. The first one, which is the crypto ingest spy, which represents the crypto ingester that fetch cryptocurrency prices from Coin Gecko API and insert them into our PostgreSQL. And the second script, which is done for testing purposes and that randomly performs inserts, updates, and deletes to simulate real-world data changes. So as we can see, we have the perform inserts that allow us to create random cryptocurrency price entries. We have the perform updates that randomly select an existing record and update its price. And lastly, we have the perform delete that randomly selects and deletes a record. We should keep in mind that these operations are chosen randomly and executed every few seconds, which provide us with a simpler automatic test generation. So let's see if all of this is actually working. So let's first run our crypto ingest.py. Oh, as we can see, we have our first inserted row at the current time. It's UTC time. This is why it is 1 hour minus my computer hour. The second row. Let's open a second window. Position. All right, the video stops for some reason. So let's recap. We have two windows. The first one where the crypto ingest shows all the insertions are done. The hour is the same as my computer. It's 1 hour minus because it's UTC. And on the other window, we can see that all these changes are fetched into Postgres in our crypto prices data. And here are the 5 last changes. So let's now see if Kafka on the other hand can catch the changes as messages. So let's first see if our topic is created, and here it is, correctly created. And let's see the 5 first messages. On the other window, the crypto ingest is still running. so that we can keep on hand in real time the working pipeline. Here it is working properly. So now the next step will be to demonstrate that all the changes are saved into HDFS files, and for that it is easier to check this through localhost 9870, which represents the name nodes and the utilities. We can browse the file system and we can find data, lake, topics, under which we have our topic with one partition. And here, as you can see, we find all our JSON files. Let's see the last one, which is created at this time according to my laptop. That's great. So this demonstrates that all the containers are working properly and that the flow is maintained from the PostgreSQL passing by Kafka and saved in Hadoop. So now let's look at how Airflow orchestrates this entire pipeline. Let's open the Airflow user interface under localhost 8080. I already log in using the admin username and password, which was admin. And in the DAX lists, we can see that we have data pipeline, DAC. I can click on it, and here we're gonna have a grid as well as graph. Here we have the code. So this has been created through this data pipeline.py that was under Airflow under DAG. This exact code, we can find it here in the code section, and it represents actually the different operators. First, we should understand what a DAG means. It means directed acyclic graph, which means tasks that moves in one direction, so no loops are allowed, and are visually representative. DAG simply means for me collection of tasks. So let's see in the grid the tasks we have and how many do we have. We have a total 5 tasks, 2 batch operators and 3 Python operators. These are simply Python functions. So let's see. Yes, here we can see that how much time I have started my DAG, the times, if the different tasks, the ones that have been successfully started, the ones that represented an error by the past, here their state at the moment. We have the graph because it is, as I said, we can have it as a visual representation. Let's zoom on it. So we have the first bash operator, which is start services. Then our 3 Python operators create Hive table, create HDFS Sink Connector, and create Debezium connector. And lastly, run test generator. So in the code, we can see that we have these 3 operators defined. Here it is. We also have the order these tasks should suit. So first we start the services, then we run the 3 Python operators, and lastly the run test generator. Yeah, in the grid, in the graph section, by here we can see that all success, here all success, all success, all success. We can run automatically and easily our pipeline by here, and here we can see that the container, the tasks, if they are running correctly or not. So it gives an easy, manageable way to tackle our pipeline and to detect the failures, the errors, if things are running or not, etc., etc. So here, and to resume our work, we have built and demonstrated a complete real-time pipeline that satisfies the majority or all the requirements. We have separate containers, as we mentioned. We have test generator, airflow orchestration, and all is working properly, and the HDFS files are saved as they should. This architecture is not only academically interesting, but also has real-world applications, and it can be applied, for example, to track historical pricing data for finance analysis, or create data warehouses that update in real time. So, thank you so much for your attention, and I am happy to answer any questions that are related to the implementation details. Thank you so much.